Can you see the
Yes,
slide?
you're good to go.
Okay, great. All right, hi everyone, I'm Sam, and today I'm going to be talking about reinforcement learning in two-player zero-sum games. And this work is from a paper of a different name, which also does some theory and some work on quantal response equilibria that I'm not going to talk about here. And this work was done with many collaborators, and Ryan D'Orazio in particular played a large role. Okay, to start off, I want to sort of explain what I mean by the term two-player zero-sum games. So in a two-player zero-sum game, one player's win is another player's loss. So you can think about it like rock, paper, scissors. If I win, you lose, we might tie. And these games may unfold over time. So in rock, paper, scissors, we just take one action and we're done. But in other games like checkers, we keep playing as time goes on. It's not just simultaneous move and then over. And lastly, these games may involve imperfect information. So for example, in a setting like poker, I can't see your cards and you can't see mine. And all of these aspects kind of play into interesting problems and how you can make decisions in these settings. So just to be a little bit more explicit, in a lot of these settings, what people classically look for is something called a minimax solution or a Nash equilibria. And this is a policy which is maximally robust to adversaries. So what I've written here is that we want a policy pi1 such that if our opponent pi2 minimizes the amount of cumulative reward we get, we still do as well as possible. And just as far as terminology, if it's the case that we're faced with a worst case opponent, people will sometimes call that a best response. And the amount that a worst case opponent beats us by is called exploitability. Does anyone have any questions about these terms? Okay. So I'm going to give you a very brief overview of the state of research on sort of coming up with good policies in two-player zero-sum games.
Sorry, a quick question.
Yeah.
The RT in the previous slide was, is it just the terminal like reward of like win or?
So it could be, but it could also be an intermediate reward. So you could imagine a game where rewards are sort of doled out over time, and we're trying to maximize the cumulative sum until the game ends. Or it could be that all of the RTs are 0 until the end, and then it's 1 or -1 or something like that.
Oh, sorry, go ahead. No, I'm just curious if there's like a special structure for your rewards for zero-sum games in general, or?
So the special structure here is the fact that we can represent it as a scalar, that one player is trying to maximize and one player is trying to minimize. In general, if the game weren't zero-sum, we would need a separate reward function for each player. So I guess like another way you could think about this is that there are two reward functions, and this is the output of the reward for player 1, and player 2 has a different reward function, which is the negative of this reward function that it's trying to maximize.
So it doesn't matter that it's like, what if the cumulative sums over both the, well, I guess if it's the same reward function, it doesn't, they always sum to 0, but
Yeah, exactly. Yeah. Yeah, so to give sort of a quick overview of the state of research in this field, there's been a lot of work in computational game theory and coming up with sound methods for solving these settings. And what I loosely mean by a sound method is something that has pretty good guarantees about converging to a Nash equilibrium. or these policies which are very hard to beat. And these include things like regret minimization, fictitious play, double oracle, linear programming, and public belief states. And it's not super important if you're not familiar with these terms. But just to give you a flavor of some of the things that people studied. And there are also methods that people are interested in these kind of games, which are very scalable, and namely sort of modern deep reinforcement learning algorithms. But the problem, which is kind of illustrated by this Venn diagram, is that the methods which are sound are not very scalable, and the methods which are scalable are not very sound. And there's been a fair bit of work over the last 5 to 10 years that tries to take the methods in this half, the methods that are sound, and sort of combine them with deep learning and make them scalable. And in some cases, this works quite well. But as a general matter, there are not really any existing algorithms which sort of converge to something desirable and also work really well at scale. So if I gave you a new large 2-player zero-sum problem, it's not necessarily that obvious exactly what kind of algorithm you should throw at it. So in this talk, I'm going to sort of tell you about how we're going to try and resolve this issue. And specifically, rather than going from this side to the middle, we're going to try and take reinforcement learning and make it into a sound method. Yes.
But by scalable, do you mean like scalable to more complex? Like, what is this scalable thing?
So I'm using it pretty loosely here because the ways in which these methods struggle with scalability varies by the method. But very informally, I mean that you can say just take some deep RL method and like run it out of the box on a very large problem. Okay, so previously I claimed that these RL methods are not sound in 2-player zero-sum games and maybe won't converge to something desirable. So here I'm going to show you an example of that. So this picture on the screen is a representation of a variant of the game rock, paper, scissors. And in particular, it's a visualization of the policy space. So for example, at this point on the triangle, it means I'm always playing rock. And at this point, it means I'm mixing 50% rock and 50% scissors. And at this point, I'm mixing equally between rock, paper, and scissors. And what I've drawn here in purple is the Nash equilibrium of the game. And I've perturbed the Nash equilibrium of the game to be non-uniform to make it a little bit more interesting. So if I ran some RL algorithm in this game, what we would like to happen is that the policy converges to the Nash equilibrium. And I'm going to show you what actually happens if we kind of naively run a policy gradient algorithm, which is that rather than converging to the Nash equilibrium, we actually spiral outward away from it. So sort of the worst thing that could happen is exactly what's happening here, in that we're ending up with very exploitable policies that wouldn't be very robust to a best responder.
So what algorithm are you running here, and like what's the reward structure? Like, are you playing two algorithms against each other, or?
Yeah, that's exactly right.
And then are you running a formal algorithm, or is this a deep RL algorithm that you're running here?
So I'm running, you know what hedge is?
Yeah.
So I'm running hedge here.
Okay.
What does hedge entail?
So it's an update equation, which I guess takes some feedback and specifies a particular policy, which is common in online learning literature.
What happens if I just run value iteration? Like if I fix, let's say I fix an optimal policy as my opponent and I run value iteration.
So, I mean, so you could think about this in the case of like standard rock, paper, scissors. So in this case, the Nash equilibrium is uniform. So my optimal opponent is uniform. And now I want to run value iteration against a uniform opponent. In a Nash equilibrium, all of the actions get an equal payoff. So that means we'll get an EV of 0 for playing rock, paper, and scissors. So any policy will be like an optimal solution. So we won't necessarily recover the Nash equilibrium. And in the case that we have a non-uniform Nash equilibrium, like an entropy breaking, tie-breaking scheme wouldn't recover it either.
I'll get back to that.
Okay. So yeah, as I alluded to earlier, the sort of main, I guess, thrust of this talk is asking how can we get reinforcement learning to work? And the sort of claim I'm going to make is that we have this algorithm that does this, which I'm going to call magnetic mirror descent. So to start off, I'm going to give a brief intro to what mirror descent is, and then later we can get into what magnetic mirror descent is. So if you haven't seen it before, I would encourage you to think about it as a generalization of gradient descent to different notions of distance. So in its most general form, it looks like this. So what's going on here is that our iterates are represented by x. And this is an update equation to go from our current point xt to our next point xt plus 1. And this update equation has two terms, this red term and this green term. This red term says we should go in a direction that follows the gradient. And this green term says I want to stay pretty close to my current point xt. So this B function people call Bregman divergence, and it will basically penalize the distance between these 2 points. And it turns out that if you plug in Euclidean distance for this B function, you will recover standard gradient descent. Does anyone have any questions about this? So in particular, in reinforcement learning, there's an instance of mirror descent that's oftentimes useful, which is this hedge algorithm, which selects this Bregman divergence to be KL distance. And in this case, it's maybe more natural for reinforcement learning people to view this as a maximization problem, where we want our next policy to place high weight on the things that have good Q values or good action values, but also not to move too far away from our current policy. And if we have discrete actions, this has a nice closed form update. And this is what people typically mean when they say hedge. Does anyone have any questions about this?
Is there a relationship between this closeness of the policies versus closeness in like learning rate updates size?
Yes, so you can think about this value here as the learning rate. So for example, if I make the learning rate very large, the weight of this term becomes very small, and we'll take a big step in the direction of the gradient. But if I make and vice versa. Okay, anything else? Okay. So now I'm going to tell you about this other algorithm, which I'm going to call magnetic mirror descent. So just as I said, mirror descent is a generalization of gradient descent. I'm going to say magnetic mirror descent is a generalization of regularized gradient descent. So similar to before, we have a term that says follow our gradient, and we have a term that says don't move too far from our current point. But now we're also going to add an additional term, which says we should try to be close to some external point z. And this external point z, I'm going to call the magnet. So to give you a little intuition for this, you could imagine that if we selected Euclidean distance for our Bregman divergence, and we selected the origin as z, this would be acting as penalization on the norm of our weights while we were doing gradient descent. So in the case that we're using this KL divergence, the update equation looks like this, where now we're using KL divergence to this external point or this magnet rho. And sort of an important special case of this equation is when rho is the uniform policy, in which case this KL divergence in blue turns into just an entropy bonus. So if you're familiar with policy gradient algorithms at RL, this equation is starting to look very familiar because we have this term which says increase our Q values, this term that says don't change our policy too much, and this regularization term. And this is spiritually similar or sometimes exactly the same as deep RL algorithms that people actually use in practice. Does anyone have any questions about this? Okay, so this also has a closed form. It's a little bit less nice than before, but understanding the details of the terms here is not important. Okay, so I said before that we're going to try and make RL sound. And I'm going to give you kind of an idea of what I meant by that now. And in particular, if we're playing a one-shot game, so a game like rock, paper, scissors, and this step size term is sufficiently small relative to the amount of regularization to the magnet that we're using, we're going to converge exponentially fast to a regularized equilibrium. So to illustrate that a little bit, I can show you a plot of
What is L?
L is a function of the payoff matrix of the game. And here it's the maximum, the absolute maximum payoff value. So on the x-axis here, I'm going to show you the number of iterations of self-play. On the y-axis, I'm going to show you the KL divergence to the equilibrium. And people call this particular kind of equilibrium a quantal response equilibrium. And it's basically the Nash equilibrium of an entropy regularized game. And you'll notice that since the y-axis is logarithmic and the x-axis is linear, exponential convergence means that we should look like a line going downward. And I'm going to show this to you for different temperatures. And what you'll notice is that we get faster convergence the higher the temperature we use. And again, this temperature term is this alpha here, which is the amount that we're regularizing toward the uniform policy or some other external policy. And the reason we get, or one reason we get faster convergence for these higher temperatures is that we can afford to use a higher step size and maintain our convergence guarantee. Does anyone have any questions about this? So we can visualize this in the same way as before, with this rock, paper, scissors game. And what I've written here now is with these stars, the locations of the different regularized equilibria. So for example, the more regularized equilibrium is in green, and the less regularized one is in blue, and the Nash equilibrium is in black. So as you might expect, the less that you regularize toward an external point, the closer the equilibrium that's induced resembles the equilibrium of the original game. And similarly to the plot we see on the left, if we run this algorithm, we get faster convergence for the equilibria that are more regularized. But of course, this comes at the cost of being further away from the Nash equilibrium. Does anyone have any questions here?
This is still a rock, paper, scissors example.
Yes.
Why is the why is the Nash equilibrium down there?
So I perturbed the payoffs of the game a little bit to make it non-uniform,
Oh, I see.
because if you're regularizing toward uniform, then obviously you're going to converge. So in this particular version, the payoffs are doubled if someone plays scissors.
I see, okay.
Okay, so on that last slide, I was talking about regularized equilibria. But I was sort of originally motivated this more with thinking about Nash equilibria or policies that have low exploitability. And we can actually do that with magnetic mirror descent too. And we can do it in two ways. One of these ways is by annealing the temperature or the amount of regularization we're using toward the magnet. So as we saw on the last slide, using less regularization gets you closer to the Nash equilibrium. So we can just keep using less and less and less regularization, and we'll get closer and closer. The other way is that we can actually change where the magnet is. And in particular, have the magnet slowly trail behind the current policy while keeping the same amount of temperature regularization toward the magnet. And as you can see here, both of these will end up giving us convergence to the Nash equilibrium empirically. Does anyone have any questions about what's going on here?
Wait, so you're saying, less regularization, you're more likely to end up at the Nash equilibrium?
So you're going to be closer to the Nash equilibrium. So like here, we're just looking at where these equilibria are located. Their distance from the Nash equilibrium is sorted by the amount of regularization that they have.
So why wouldn't
So-
you diverge like in the naive self-play setting?
Sorry,
Why wouldn't you diverge? Why are you still able to go to the Nash?
when you anneal?
When you do this regularization, if you're, I guess like, I'm getting confused because you're saying if you do less regularization, that means you're more likely to end up at the Nash, but doesn't that end up back in the setting of the standard RL algorithm?
Yes, that's a good question. So I guess maybe something informative here is to look at this equation for our convergence guarantee. So we can think about if we want the exact Nash equilibrium, we could make this regularization 0. And then to guarantee that we would not decrease the performance, we would have to select our step size to 0. And what selecting our step size to 0 means is that we're placing infinite weight on staying close to our current policy, and actually like we're not going to move at all.
Oh, I see. Okay.
So sort of another way you could view it is that as we use less regularization, these lines are going to keep getting flatter and flatter and flatter until we hit 0, and then we're just flat. But what we can do is compute this equilibrium and then lower the temperature a little bit and compute this one, and then lower the temperature a bit and compute this one. And that way we're getting closer and closer and closer, but we're never actually hitting zero regularization. Any other questions about this?
So in your setting, you generally anneal temperature and then allow learning rate to follow due to that equation.
Yes, that's what this blue trajectory is doing here. The orange one is keeping the same amount of temperature regularization and changing where the magnet is. So this square here is the location of the magnet, and it's just slowly following behind the current policy.
The guarantee that you have doesn't depend on where you place that magnet.
The guarantee doesn't depend on where the magnet is. That's right. Okay. So far I've sort of focused on this kind of rock, paper, scissors setting, which is this kind of game where we both take an action and then the game ends. But in general, we're interested in algorithms that are going to scale to very large games. And in these large games, the course of the game unfolds over time. So it's not just that we take an action and we're done, but we take an action and then they take an action and then we take an action and so forth. And at least as far as solving small and medium-sized games, the kind of gold standard algorithm for this setting is something called counterfactual regret minimization. So I'm going to show you here a comparison for trying to solve these smaller games as opposed to counterfactual regret minimization. So these are four sort of classical benchmark games. On the x-axis, I'm going to show you the number of iterations that it takes. And on the y-axis, I'm going to show you the exploitability. So lower is better, and if you get all the way down to zero, you're at a Nash equilibrium. And I'm going to show this to you for four different algorithms. Two are the ones I just showed you, which is magnetic mirror descent with annealing the amount of regularization we're using, and magnetic mirror descent where we're slowly having the magnet trail behind the current policy. I'm going to also show you against sort of the standard CFR algorithm and CFR plus. And CFR plus is maybe the state of the art or among the state of the art algorithms you might use to solve games like these.
If you give intuition on what CFR plus does.
So if you're familiar with regret minimization style algorithms, it's based on that. So these are the results. What you can see is maybe first that it seems like CFR plus is definitely the best still. But what's quite encouraging about these results is that particularly magnetic mirror descent annealing the temperature is pretty reliably competitive with standard CFR. And this is a pretty exciting result because historically, there were not even any reinforcement learning algorithms which could make these lines go down in these settings. So we wouldn't get convergence at all. So the fact that we can get tabular convergence, which is competitive with CFR, is something that I'm very excited about. And then with the moving magnet, what we can see, which is kind of interesting, is that it's relatively slow to get started, but ends up getting what looks like exponential convergence in the end. Does anyone have any questions about this slide?
So how are these benchmarks set up? Are you playing against like a fixed algorithm or is algorithm of its own version? Like...
So the algorithm is controlling the updates for both players.
I see.
And then you measure the exploitability of the joint policy.
So you run two copies of the same algorithm? When
people talk about CFR, like running CFR in a game, the like sort of implicit understanding is that like all players are being controlled by CFR. So people would think about it not even as two copies of the same algorithm, but just that that is what CFR does when they say it unqualified.
So that just means if this number goes down, you can find an equilibrium. But you're not guaranteed that that's like an optimal solution for the problem, right?
So the exploitability is not, this is not the performance against the other agent
Oh,
you're
I see.
learning
Okay.
from. This is if I extract the thing that I was training and then compute a best response and measure how well the best response does. So if this goes to 0, we really are doing something that's good in a more general sense. But sort of the nice thing about the setup is that to actually come up with this policy, we can just run something against itself and we don't have to stop every time step and compute an exact best response. Does anyone have any other questions about this? Okay. So it's great that this is competitive against CFR, but the sort of real motivating thing for this is now that we have a somewhat more sound RL approach to these two-player zero-sum games, can we make it scale up to large problems with deep reinforcement learning? And sort of as we were discussing when we were looking at the update equation, the update equation for magnetic mirror descent is either spiritually or almost exactly coincides with deep RL algorithms that people use in practice, like PPO, for example. So it's relatively easy to implement as a deep RL algorithm. So I'm going to show you some results for deep RL. And on the y-axis, I'm going to show you an approximation of exploitability. And I'm going to show you for 2 different games. And I'm going to show you for a number of different algorithms. In blue is going to be a deep RL version of magnetic mirror descent. In orange is going to be an algorithm which was inspired by making these sort of sound methods scalable. In green is an example of what happens if you naively run RL. And then I'm also going to show you a bot which just takes actions at uniform random, and one that just always selects the first action available to it. So here's an example of what the plots are going to look like. So what this is saying is that I ran 5 runs of the deep RL version of magnetic mirror descent. And this is the approximate exploitability at 1 million time steps. And this is it at 10 million time steps. Does anyone have any questions about how this plot is set up?
How do you approximate exploitability?
So I'm training a best response using reinforcement learning for a long time. So this is a lower bound on the exploitability. But these games were specifically selected such that you can get a pretty reliable estimate using this kind of lower bound technique. So here are the results for the other methods. The first thing that maybe you'll notice is that the bot that always selects the first legal action gets a approximate exploitability of 1. So this means that it's perfectly exploitable and loses every single game against the best response. So this is quite poor. In contrast, even doing something as simple as taking actions uniformly randomly can get you significantly better in terms of your robustness to worst case opponents. And what you'll notice is sort of reflecting our earlier sentiment about how naively running RL isn't very principled, is that our RL algorithm, which is in green, actually over the course of training becomes perfectly exploitable. So it's not really behaving the way we would want it to. And while this algorithm, which was inspired by these tabularly sound algorithms and made scalable with deep learning, does decrease the exploitability over time, the speed of learning is much, much slower than just running the deep RL version of magnetic mirror descent.
Can I follow up on like how you compute the optimal policy then?
So
you
there's
said you use deep RL, but deep RL doesn't seem to work if you're trying to connect.
So there's no optimal policy. What I'm doing here is computing a best response. So this is a single agent problem. So I'm stopping training, say for this run, and I'm holding one player fixed as this player. And for the other player, there's now a single agent deep RL problem of beating this player as badly as possible.
I see.
So the best response problem is something that existing methods in games like these are very good at. And in this other game I'm going to show you, you see something similar, except maybe more extreme, where compared to the amount of progress that magnetic mirror descent makes, these other algorithms, to the extent that they're learning to reduce exploitability at all, are doing so very slowly. Does anyone have any questions about this?
Wait, sorry, you were saying that magnetic mirror descent is like, in essence, kind of has the same flavor as PPO, but then, so what's the difference between the two?
So the sort of important, that's a great question. The sort of important difference is the kind of spiritual sort of inequality, that the spirit of the inequality that I showed you earlier, which is that to have stability, you need to have high regularization or to use a really small step size. So the amount of regularization that's being used here is much larger than someone would typically consider using for an RL algorithm like this. So it's not so much that you need different algorithms, but that you need to consider different hyperparameter regimes.
Oh, okay.
Though in tabular settings, actually, the exact update form of this versus this makes a difference. But when you scale to deep RL, everything becomes so approximate that it's not as important. Okay, any other questions? Also in these games, while we would like to have a Nash equilibrium, we're not always playing against a worst case opponent. So if we're not actually at a Nash equilibrium, it doesn't just matter how badly we do against a worst case opponent, but also kind of how badly we do in practical situations. So to the spirit of that, I'm going to show you results for head-to-head matchups. And I'm going to show you the same algorithms and the same games. And how I'm structuring this plot is that the agent I'm going to show you the results for is on the x-axis. So if the plots here, if the points here are above 0, it means this agent is winning. And if they're below 0, it means this agent is losing. So to give you an example, in this game for magnetic mirror descent, it's beating the bots that take actions uniformly randomly and arbitrarily by a significant amount, and winning or tying against the RL algorithm, and winning against the NFSP algorithm by a smaller amount.
At what point in time is this?
This is at the 10 million time step training regime. So what you'll notice here is that whereas we're pretty robust against these sort of non-adversarially selected opponents when we use magnetic mirror descent, when we use these other algorithms, which didn't do as good of a job minimizing exploitability, we kind of end up all over the map in terms of whether we perform well in head-to-head matchups. And what that means is that, for example, sometimes they beat opponents quite badly, and in fact, more so than magnetic mirror descent might beat the same opponent, but other times they'll lose against other opponents quite badly, much worse than a lower exploitability policy would have lost against them. And in phantom tic-tac-toe, we see again a sort of similar version of the same phenomenon, but maybe a little bit more exacerbated, where none of the other policies are even managing to tie against magnetic mirror descent. Does anyone have any questions about this slide?
So in the second thing, PPO is actually losing to the arbitrary policy.
Yeah. In phantom tic-tac-toe, what the arbitrary policy is doing is just trying to get 3 across on the top row. So you could think about it as kind of like a rush attack. So unless you're sort of mixing enough to defend against that, you're somewhat vulnerable to it. And just sort of naively running RL, if you remember, you risk kind of diverging to the edge of the simplex. And so you might be focused only on one area of the board and totally ignore it totally ignore, say, the top row in such a way that even doing something very stupid, for example, as rushing the top row, is pretty effective. So that like kind of is a good illustration of the fact that naively running RL in these games with imperfect information can really be quite bad if you're not careful. Yeah, so that is, I guess, the content that I wanted to present. So just to sort of summarize the presentation, historically, in the last 5 to 10 years in this field, there was this kind of separation between methods that were obviously sound and methods that were obviously scalable. And the reason why I'm excited about MMD is that you kind of get the best of both worlds. I guess I can take any additional questions.
Yeah, open up for questions. Thank you for coming to speak. So how do you come across these? So if it's a difference between parameter tuning, so like say I was to work with PPO, so how would I pick these hyperparameters to make it in the setting of MMD?
So I guess the sort of spiritual takeaway from this is that it makes sense to consider more entropy regularization than you would perhaps ever think to use in a single agent setting. So it doesn't, like, to measure whether it's working, you would still have to try a bunch of different levels of entropy regularization and test their performance with your desired criteria. But I think the takeaway from this is that you should be trying more entropy regularization than you might think to otherwise.
I also saw that you had it over one point, like you can have entropy, like that alpha term could be larger than 1.
Yeah, so the scale of the amount of entropy regularization depends on the scale of the reward as far as what makes sense. Okay. So if you have rewards scaling from, if you have like returns that run from, run up to the thousands or 100,000s, that might not be a good idea for other reasons, but say you did, then an entropy regularization of 1 would be quite small.
Yeah.
Because it's really just relative to the scale of the rewards.
The actual rewards, yeah.
Which I guess in some ways it makes it a little bit difficult to give like sort of general advice as far as what value is like good enough, because it really depends on the problem setting.
But that's something that we have for practical algorithms too, right? Like SAC has exactly this phenomenon, like. Yeah, are supposed to scale with the largest relative user.
Yeah.
Do you think like some form of like explicit opponent modeling is necessary to improve like head-on performance? Like, I'm just trying to think like what's the way to get the best of both? One where you're not that exploitable, but also maybe, you know, set up like traps and chess where you can like exploit some opponent's weakness in particular.
Yeah, that's a good question. So in chess, it doesn't necessarily make that much sense, in the sense that if you get sufficiently close to a Nash equilibrium in chess, you're going to beat everyone, at least humans. But yeah, in general, kind of interpolating between exploiting particular opponents and being robust to worst case opponents is a pretty interesting research problem. If you've seen some of the recent work on diplomacy that the group at FAIR did, I think they have some pretty interesting ideas for how to handle that.
Was this specific to like 2-player games? What if I increase the number of players?
It is, in the sense that 2-player games have this very nice property where if I'm playing a Nash equilibrium, I get a guarantee that I'll do well no matter what you do. But as soon as I say do 3 players or the game is not zero sum, like all of those bets are off, where I can be playing a Nash equilibrium, and if you do something else, I might still do quite badly in the game. So beyond these 2-player adversarial settings, you need to be a bit more mindful of what your opponents are likely to do. And it's trickier to handle sort of prescriptively how you should play in an opponent agnostic way. But again, this recent work that this team at FAIR did on diplomacy, diplomacy is like a 7-player game.
Yeah, that's
And so they have roughly what they did was like involved data from human players online, and using that data to get an idea of what their opponents might look like, and sort of balancing between trying to exploit that data while also not overfitting to it.
But I guess that makes it a 2-player game. Which is probabilistic attack, I guess.
Well, it depends. The way they did it was still having the players sort of all do search in their own interests, but they were just regularized toward their, like, the data that was observed online. So you could think about it also maybe in some ways as like trying to push the kinds of policies you're learning toward a particular subclass of regularized equilibria, so you don't end up at a totally incompatible equilibrium from the ones that your opponents are playing.
How well does this look like a single player? Like, if you fix your opponent and then you just use this to train rather than like do it the other way around.
Yeah.
It'll still work.
Yeah, this would still work. I mean, like this flavor of algorithm is very similar to the policy gradient algorithms that people actually use. So, and you would expect those, you know, to do fine in single agent settings where you fix an opponent. There is a kind of problem that you run into in some settings. So for example, if I trained an agent that was really good at Go, and then you tried to train a best response from scratch, you would lose every single game. So you wouldn't really get very good learning signal. So you sometimes have to be a bit careful about training best responses in that sense. But Not in the, it's just a single agent problem, so it's, I guess, sort of the norm otherwise.
Yeah, I'm just trying to think of if there's like an algorithm that does this, but I don't think there is, right? Like
What do you mean by this?
PPO is like, I'm thinking about like how, what would this look like as a deep RL algorithm, just for like a simple idea.
Well, yeah, so let me go back to the update equation.
And like PPO is missing, like,
So PPO,
is missing.
essentially has this term,
Yes.
and it essentially has this term where you pick this to be uniform. And the
That's-
kind of regularization that it was motivated by is KL in the opposite direction, which people sometimes use. And a lot of, I think there's some evidence in deep RL that if you're doing this KL regularization, at least in discrete settings, the direction doesn't really matter very much. What they actually do a lot of the time with the gradient clipping is a bit more qualitatively different.
Yeah, that's what I mean, right? Like nobody actually computes this. Like they just say, well,
Yeah,
hopefully this is roughly this, but like nobody actually computes it. I guess TFV kind of tries to, but
well, that's still for the other direction of the KL.
yeah, it's still the wrong direction.
I mean, you can do this, and the performance is, if you tune the hyperparameters, like pretty similar to what you would get with PPO. Like whether it's worth like changing the algorithm just because you have nice guarantees and tabular settings is a little bit unclear.
That's fair.
But yeah, if you ran this as a single agent RL algorithm, it would be fine.
Where do you see your future work going?
I think it would be cool to maybe demonstrate. So these games that I'm showing here, were selected specifically to be large enough that they're interesting, but small enough that we can actually get a good idea. We can actually approximate this quantity pretty well. Because once you go too large, it becomes pretty hard to approximate exploitability. So I think it would be cool to show that these kinds of methods can scale to much larger settings in an interesting way.